Evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my latest training video. For this particular training video, we're going to take a look at severe weather fundamentals. Now, this is going to be severe weather fundamentals part 1. I will then move into severe weather fundamentals part 2 on another day. We'll just cover this one for this evening, severe weather fundamentals part 1. This is really going to focus in more on the convective type of severe weather, such as thunderstorms, tornadoes, and that sort of thing. So I certainly hope you enjoyed the video. This is a great opening title slide, by the way, with this tornado basically in contact with the ground here, touchdown right in this location here over an open field. This is a really nice shot. But let's go ahead and get right into the training. So for the overview, one of the biggest overviews of severe weather in particular is it's one of the most fascinating aspects of weather. It really captures our attention. From thunderstorms development to tornado genesis, which is really a fancy way to say tornado development or formation, every year convective storms cause fatalities as well as property damage. And on average, by the way, there's about 1,800 thunderstorms producing 100 lightning flashes per second that is in progress. Now, thunderstorms vary from a brief shower to ones that produce winds greater than or equal to 50 knots, as well as those that have large damaging hail. So there's a wide range of thunderstorm types out there. For convection in general, this is just a quick training refresher on convection. I did cover convection in the past, so feel free to look back at my previous training videos here on the Spot On Weather YouTube channel. Just a refresher here. Convection is basically that vertical transport of air, most importantly, upward vertical motion in the atmosphere. And as air rises, it tends to expand and it tends to cool, eventually reaching saturation, where we talked about the temperature and the dew point are the same. And that leads to 100% relative humidity when you reach saturation. And with that being said, we see a cloud form. Now, there are two types of convection. We talked about this in the past training video. We talked about free convection as well as forced convection, with free convection pretty much occurring when you get a heated surface during the summertime. The air rises due to this being less buoyant, that warmer heated air rises. Positive buoyancy exists in the atmosphere in this case. So on hot summer afternoons, when you get those pop-up summertime thunderstorms, that is an example of free convection. There's nothing forcing the air to rise in the vertical. Forced convection, on the other hand, does involve something coming in, whether it be a mountain, some form of topography, or a front itself coming into an area. We just talked about fronts in my last training video. So forced convection, fronts coming in. We talked about how with fronts we have rising air motion, that warm, moist air rising, particularly ahead of cold fronts. And again, orographics, topography, however you want to frame it, mountains. Additionally, with convection, air also rises due to low-level convergence. That can also result in convection, upward vertical motion in the atmosphere. Now let's turn our attention to thunderstorm requirements. Just the basic bare bone requirements for thunderstorm development. First things first, we must have the air mass fairly unstable. The warm, moist air must be there. It must be available to be lifted in the atmosphere to begin with. And then we need some type of low-level lifting action that's in place. It could be free convection, where you have intense heating of the surface on a summer afternoon. It could be the front coming in. But we need some form of lifting action or mechanism in place to cause this air to rise in the vertical. And basically, we get these convective air currents to develop. All right, so I like to kind of think of basic thunderstorm requirements as lifting, instability, and moisture. You need those three things. L-I-M, limb. Lifting, instability, and moisture. I'll go ahead and spell it out for you. So L, and this is the letter I, and then the letter M. That's going to basically give you the ingredients for thunderstorm development. If you look over here in the upper right, I wanted to just really point out a couple things here. We have an unstable air mass, by the way. We talked about this first bullet. What makes an air mass unstable? Well, it just simply, you take a look at what's going on with the temperature profiles from the surface or the ground upward in the atmosphere and the vertical. Now, if we have colder air moving in the upper levels of the atmosphere over a warm, moist surface, that is going to destabilize or make the atmosphere more unstable. We have warmer, moist air at the surface. That's going to be less dense. It's going to want to rise, and you see that by these red upward directed arrows. That indicates that warm, moist air wanting to rise. With colder air in the upper levels above it, you have air that wants to be sinking because the air is more dense with colder air. So colder air sinks, more dense. Warm, moist air beneath it, air wants to rise. So basically we have a situation where there's no equilibrium and we have an unstable atmosphere. Bottom right here shows, again, the various mechanisms in which we can get this convection, these convective currents to develop. The first one on the bottom right here, on the left side of the bottom right graphic, we have a cold front moving in, so a frontal system. We could have orographics or mountains where we have heating along the windward side. As that wind blows up against the windward side of the mountain, the air is going to be forced to rise up that windward side of the mountain, resulting in thunderstorms. And then over here on the bottom right, we have low-level convergence air. So basically, air that is just converging in the low levels. When the air meets in the low levels, it's forced to go upward. Now, an important consideration with atmospheric stability, this is one of the big keys we look at for thunderstorm development. And again, stability refers to a condition of equilibrium. I kind of hit it right here, the stability of the atmosphere. If you have a stable atmosphere, you generally have warmer air above cooler air. Okay, I'm going to go ahead and put that. Let me go ahead and move on here. I got a little acronym for you in a minute. So, atmospheric stability refers to a condition of equilibrium. We have warmer air above cooler air at the surface. So, warm above cold. Here we go. Let me just draw this out right now while I'm thinking of it. So, when we have stability, I like to do the acronym WOC, okay? WOC. And that is warm temperatures over colder temperatures. That is a stable situation in the atmosphere. We want to determine stability, by the way, by comparing the temperature of a rising air parcel to that of its surrounding environment as well. And before I go any further here, I know I'm getting kind of sidetracked here. I want to do one more thing here. So before I move on to these next bullets, and we'll talk about comparing air parcels to the surrounding air temperatures in the environment. Again, this is, here, let me just do this here. Warm temperatures over cold is stable, like I've already mentioned, so that we'll just put stable here, right? That's a stable atmosphere when you have warm air over cold air, all right? Cold air is heavier, it wants to be lower. Warmer air is lighter, it wants to be above the cold air, and this is a perfect example of stability. On the other hand, to get unstable in the atmosphere, don't tip the cow. When I went to meteorology school, that's what we used to say. You never want to tip the cow because the cow is unstable, right? So what this represents, the acronym COW for unstable, is cold air over warmer air. This colder air is heavier aloft, it's going to want to sink. The warm air is lighter, less dense, it's going to want to rise. So we have vertical air currents going on, and this is going to be an unstable atmosphere when we have that situation. So meteorologists will look at skew-T soundings, which are these vertical profile soundings. They'll look at forecast soundings, and they'll determine, hey, what is the temperature profile in the vertical, or what it's forecast to be for a particular day. Okay, now that I got that out of my system, let's go ahead and continue on with these bullets here for atmospheric stability. Okay, so again, refers to a condition of equilibrium. You determine the stability by comparing the temperature of a rising air parcel to that of its surrounding environment. I did talk about that in the cloud formation and dissipation training video. Take a look at that when we talked about air parcels rising at various rates in the atmosphere. One was an unsaturated rate, known as a dry adiabatic lapse rate, where the air parcel rises and cools at 10 degrees Celsius per kilometer. And the other is the saturated or the moist adiabatic lap rate, where that air parcel is going to rise at 6 degrees Celsius per kilometer. And I talked a lot about adiabatic processes, air rising and sinking. As it rises, it cools. As it sinks, it warms. And then comparing the air parcel temperature to the surrounding environment. So bottom line here is an unstable atmosphere. When it occurs, the rising air parcel is always going to be warmer than the surrounding environmental air. And because of this, with a warmer air parcel as compared to the surrounding environmental air, that air parcel is going to want to continue to rise in the vertical until it reaches that same temperature value as its surrounding environment. When looking for an area of thunderstorm formation or development, you should definitely consider the stability of the atmosphere. So that's kind of like what we're getting at here. Where are your warm layers? Where are your cold layers in the vertical profile of the atmosphere? Let's say, for example, the top example with WOC, W-O-C, indicating stability. Let's say I have an inversion where the temperatures are warming with height. That is generally going to result in a stable situation. You're just not going to get a lot of rising vertical air motion with an inversion, with a warm layer, let's say at 5,000 feet over a colder layer at the surface. With cow, colder air over warmer, let's say that now you got colder air advection moving in at 18,000 feet, 500 millibars, and you got a heated surface. That is going to result in convective currents setting up rising air motion. Okay, so getting into atmospheric stability a little bit more, this is showing you just on the left here. Let's just look at the left one here, the left diagram. All right, you see we have the surface indicated by the solid horizontal black line. These are your air temperatures. Basically, as you go to the left on this diagram, we have cooling air temperatures. If you go to the right, you have warming temperatures, okay? So let's compare this little red dot, all right, on the left-hand side here. This little red dot is your imaginary air parcel, all right? We look down, just draw a line straight vertically down from where the air parcel's at, and that temperature, let me go ahead and get my pen out here. This right here, let's just draw a straight vertical line down from where the air parcel is. That temperature is about 6 degrees Celsius at that level, the air parcel temperature. Now, what is the surrounding like? The surrounding environmental air is, we have to examine it at the same level by this red X. So my air parcel temperature is about, oh boy, that's rough. I'm sorry, guys. It's about 6 degrees Celsius. That is my air parcel temperature. And then the environmental air temperature is actually looking like it's about -2 Celsius. So +6, we're warmer. The air parcel is warmer than the environmental air represented by this black solid line. So guess what's going to happen? This parcel is going to continue to rise in the vertical. This is an unstable situation. I'll make a U for this. That's unstable on the left. We look over here on the right now, this right-hand diagram over here on the right, notice the air parcel, okay? If I draw a straight vertical line down from that parcel, it's not completely straight, but you get the point. I'm sitting at about an air parcel temperature of, what is that, -13? Yeah, about -13 degrees Celsius. Okay, so my air parcel temperature is -13. Now let's go straight over to where at that same vertical level, let's compare the environmental air temperature represented by this dark black line. And the environmental air temperature in this case is, what is that? Draw a line straight down. It's about -2 or so. So environmental temperature is -2 degrees Celsius, but my parcel is -13 Celsius. So my parcel is colder than the surrounding environmental air. That's going to result in a sinking air motion of that air parcel. This example on the right is stability. I'll make an S for it. So hopefully you understand when you look at atmospheric stability, you're going to compare the parcel of air. If that parcel of air is warmer than its environmental surrounding temperature, then it'll continue to rise. You got unstable conditions. Okay, the letter U here. On the right, again, air parcel temperature is colder. It's going to be heavier. It's going to be denser. It's going to want to sink downward in the atmosphere because it's colder. The air parcel temperature is colder than the environmental surrounding air of -2 at this level. So hopefully you kind of understand what I was doing in this process of analyzing the stability using these two graphics, showing an example of unstable conditions on the left, Stable conditions on the right. Why is unstable so important? Because that's going to cause the air to rise in the vertical. It's going to set up convection, potentially thunderstorm development. And whereas over here on the right, your air is going to sink. Boy, that is a rough looking arrow, guys. I do apologize for that. Stable conditions on the right hand side. So now let's examine another lifting process in the atmosphere. Let's talk about free convection. Again, it's simply caused by warm air rising without any external forcing mechanisms or influences. So with free convection, guys, we're not going to be relying on fronts or the mountains. This is just simply this warm, hot sun sending a shortwave solar radiation to the surface, and then the air rises and converges at the surface, okay? So heating of the surface by the sun warms the air in the low levels of the atmosphere down here, okay? Causes the air to rise in the vertical, setting up convective air currents or convection, development of puffy cumulus clouds. Sometimes these puffy cumulus clouds will continue to grow taller and taller and to eventually form into a cumulonimbus cloud or a thunderstorm. Now, with warm air rising, air is being replaced at the surface through the process of this low-level convergence. That's what these red arrows represent, is low-level converging air. Now, this free convection is most likely going to be happening in the summer, when we have the most intense incoming shortwave solar radiation. Forced convection, on the other hand, this is caused by mechanical lifting action. It would include a frontal boundary, okay? We have that happening right now where I'm at today. As a cold front moves into the area, it's moving into an area that has warm, moist air ahead of it, and we've seen a lot of showers and some scattered thunderstorms. A more unstable atmosphere today where I'm at because of the frontal boundary and mechanical lifting action, forced convection. Air can be forced aloft by mountainous terrain. We talked about if you live near mountains, there could be some orographic lifting going on. It really gets down to this. Say this is your mountain. These are your winds. And the winds cannot go through the mountain like this. Those winds are forced to rise and go up and over the mountains. And in that process of rising air motion on the windward side of the mountains, you get some sort of forced convection. Possible thunderstorm development on this windward side. And then also there's some type of low-level convergence. So in this example over here in the bottom right, what do we got going on here? Let's analyze it. All right, so let's say you're at this point where the X is. We have 30 knots of wind. So that's 30 over here. 30 knots of wind is moving in from this direction, from left to right in the bottom right-hand graphic. And then that 30 knots of wind is running into a wind speed of only 10 knots. So this is what's known as speed convergence, where faster moving winds, this 30 knot wind is blowing into slower moving winds, which is only 10 knots. I like to use the example of when you're on the interstate and you're approaching a toll booth where you got to pay. You're going pretty fast, right? You're going pretty fast, about a mile to 2 miles, approaching the toll booth. You're still 1 to 2 miles out. Your speed might be 60, 65 miles per hour still. But by the time you get up to the toll booth, you start converging with slower moving cars ahead of you. So those are the cars that are paying at the toll booth, right? So there's an accumulation of cars or speed convergence. Faster moving cars are going to eventually bump or slow down behind slower moving cars. So I like to use that toll booth analogy when we talk about speed convergence. All right, now let's examine the thunderstorm stages of development. Let's examine the cumulus stage, the mature stage, and the dissipating stage. These are the 3 stages of thunderstorm development. Starting with the cumulus stage, this is the first stage of thunderstorm development. Cloud is mainly going to be composed of updrafts. So these dark arrows on this graphic on the left are showing this cumulus cloud that has formed. So this is the cumulus stage. These dark arrows pointed upward indicate updrafts only in this stage. So this is upward vertical motion. This is convective currents. These are updrafts. Precip forms, but it is being held aloft by these updrafts. Now the strength of these updrafts varies, just depends on what your atmospheric instability is like. The greater the instability, the more unstable the atmosphere, the stronger these updrafts are going to be. Cumulus clouds appear generally in the sky like white puffs of cotton, and they begin to grow into rising towers or domes. So on a hot summer day, maybe you start seeing these cumulus clouds. Next is the mature stage of thunderstorm development. So now notice in the diagram here on the left, we have upward directed arrows and downward directed arrows. So this is indicative of updrafts on one side of the cloud and downdrafts on the other side of this towering cumulus cloud. This is a tall cloud. You have rain starting to come out, heavy rain showers occur during the mature stage as this downdraft of air basically forces all the precip that was being held aloft outward and down to the ground. So the precip grows larger, updrafts can no longer hold them. These downdrafts kind of take over on this side of the towering cumulus cloud and you get heavy rain showers. And with this downdraft of air, you get a general cooler feeling. The temperatures can drop rather drastically in the heavy rain shower activity associated with a thunderstorm as this precipitation drags a cooler air from aloft from the cloud down to the ground. The start of the downdraft itself is the indicator of the mature stage. And the mature stage has the most violent weather. You're going to have very gusty winds with these downdrafts. Again, very heavy rain showers. You'll see vivid displays of lightning as well as loud claps of thunder. And then finally, with the mature stage, we need to talk about one more thing. Hail is possible during the mature stage. And the way hail forms is you have strong updrafts. Let's go back to this diagram. These upward directed arrows, right? The more unstable the atmosphere, the stronger the updrafts, the greater the probability of large hail, because these updrafts are so strong, they hold up the hail in the upper portion of the cloud and kind of cycle that hailstone through the cloud. Strong updrafts will carry small hail high above that freezing level where the temperatures are below 32 degrees Fahrenheit, and then eventually will fall only to be lifted again by other strong updrafts. Each time the hail goes above and below the freezing level, it grows. It adds another layer. It's an accretion of ice process. And when it becomes too heavy for the updrafts to support it, the hail eventually falls to the ground. Let me draw, oops, I'm getting ahead of myself. Let me just kind of show you the pattern of hail formation real quickly using this cloud on the left. So with hail, generally what you get is, you notice this is 0 degrees Celsius here. That's your freezing level. This red line is your freezing level. Anything above this red line is below freezing, below 32 degrees Fahrenheit, or below 0 Celsius. Anything below this freezing line is above freezing. So you get hailstones that are going to form here. I'm just going to make little circular ball shapes here. The updrafts are going to carry these hailstones to the upper portions of this developing thunderstorm cloud. And then you're going to see the hailstone descend like this just to get picked up by another updraft and go up again. And so this hailstone keeps getting larger and larger and heavier until the downdrafts finally just push it out of the base of the cloud. These updrafts can no longer hold the weight of the hailstone up in the cloud. So the pattern, small hailstone, that goes up below freezing, above the freezing level, drops back down, goes back up, drops back down. It's like this kind of pattern of hailstone growth, ups and downs all the way, if this was your hailstone here. And every successive time this hailstone goes up into the below freezing level, higher upper reaches of the cloud, it accretes another layer of water which freezes, and you can literally count the number of trips of a hailstone by just dissecting how many layers, distinct layers there are of the hailstone. You can see how many trips it made up and down in the cloud. So that's kind of a cool thing. With hail formation again, the size of this hail is really going to be dependent. It's really going to be dependent on the strength of the updraft. Stronger updrafts, like we're showing here in the diagram on the right, you get a very strong updraft that's going to support larger, more destructive hailstones. Notice the height of the freezing level on this diagram. Now we got a full anvil at the top of this cloud. See this flat anvil hammer shape here at the top of this cumulonimbus cloud in this diagram? But you're getting really strong updrafts in this case. Looks like they're tilted updrafts. They're not straight up and down vertical. And you notice how your recycling of the hailstone, see this circular pattern I was just talking about? Below the freezing level, the hailstone partially melts, goes up, adds another coating of ice, comes down, adds water, add another coating of ice. So the height of this freezing level, by the way, is very important. If the freezing level is closer to the ground, you'll get hail that will not melt during its descent. All right, so places like Colorado, where you're already at a higher elevation, you're closer to the freezing level. There's less time for that hail to melt before it hits the ground. Places like Wyoming, mountainous areas, they are closest to the freezing level. And so you're really just going to get really large hailstones in these locations. Finally, we talk about the dissipating stage. Now, this is the final stage of thunderstorm, the thunderstorm life cycle in general. It generally occurs 15 to 30 minutes after the mature stage, and it generally is going to be dominated solely by downdraft. See the downward directed black arrows here in the diagram on the right? So completely downdraft at this point. Basically, this thunderstorm is raining itself out. There's no more inflow of warm, moist air, which is actually the energy source to keep this thunderstorm going. Now it's just dominated by cooler downdraft air as all the rain kind of rains itself out, like I mentioned. No more fuel source. Warm, moist air is no longer available, and the storm collapses with precip intensity, eventually lightening up. Okay, now let's examine the different thunderstorm types. We just talked about the thunderstorm life cycle. Now let's examine the thunderstorm types. We have 3 types we'll talk about. Air mass thunderstorms, you see a lot of these in the maximum heating time of the day, in the afternoon into the early evening in the summer months, specifically in the southeastern U.S., as well as up the eastern seaboard up towards the mid-Atlantic. Frontal thunderstorms, we'll talk about those, and we'll talk about the orographic or those mountainous thunderstorm types. With air mass thunderstorms, they're just generally going to form. You got a combination of intense surface heating. That sun is really strong in the summertime. You get low-level winds converging as the air rises. Those low-level converging winds kind of come in and fill that void of the rising air as it goes up. Thunderstorm development is enhanced when you get upper-level divergence above the developing thunderstorm. And thunderstorm cells, generally with air mass thunderstorms, are fairly small. Their diameters are less than 10 miles. And again, these air mass thunderstorms, common in the southeastern U.S. in the summer. The Bermuda High is positioned over the Atlantic Ocean, and on the back side of that Bermuda High or that subtropical ridge, you're getting a large amount of moisture supplied. Intense solar heating along with that large amount of moisture is a great recipe for thunderstorm development. The life cycle of air mass thunderstorms is pretty brief, lasts 1 hour or less as precip eventually in that dissipating stage chokes off the updraft rather quickly. Frontal thunderstorms, on the other hand, these are associated with fronts. As the name implies, they're frontal. This occurs with forced convection processes. Front is one example of forced convection. And for the frontal thunderstorms, they commonly form in lines, and the development of multi-cell storms are more violent when compared to air mass thunderstorms alone. Here's an example of frontal thunderstorms. Are more common with cold fronts, typically out ahead along the leading edge of cold fronts. With cold fronts, the upper level dynamics are just much more stronger as compared to warm fronts. You will get a squall line feature. Look at this graphic on the right. I showed this, I believe, in my last video. We talked about inactive, fast-moving cold fronts. That's what these squall lines are associated with. So 50 to about 150 miles ahead of these inactive, fast-moving cold fronts is where you get frontal thunderstorms. They usually form a line. There'll be a line shape to them. Squall line is characterized by cumulonimbus clouds, which are your thunderstorm clouds, strong gusty winds, as well as possible tornadic activity. You can get tornado development sometimes in the leading edge of these lines. One other thing I wanted to mention about frontal thunderstorms, we talk about squall lines in general. Sometimes you get a shape that's like this. Sometimes the reflectivity is going to look like this. And where this thunderstorm kind of juts out, or where there's a bow feature, this is called a bow echo. And wherever this thunderstorm shape bows out, now let me do another one. I'll make it more apparent for you. So see this area here? If this was a line of thunderstorms here, where that bows out, that is where you're going to have the strongest, potentially damaging wind gusts with downdraft winds with a line of thunderstorms. So I just kind of wanted to throw that out there. Then finally, we have orographic thunderstorms. Now, these are going to form in mountainous regions, as the name implies, or orographic implies higher elevation or terrain. It's a force lifting mechanism, force convection. Again, you get the strong winds on the windward side. They're forced to go up the windward slopes, and you get thunderstorm development. If the wind's blowing upslope and there's moisture available, of course, you have to have that moisture, and you get an unstable condition, then you definitely get orographic thunderstorms. Now, with thunderstorm characteristics, let's talk about this now as we switch gears a little bit. Now, thunderstorms are associated with a cumulonimbus cloud, abbreviated by the letters CB. Sometimes you'll see these pouch-like clouds on the underside of cumulonimbus clouds. Now, these are really cool. A lot of folks take pictures of these. They're just amazing to look at. And those are known as cumulonimbus mammatus. Let me go ahead and bring my laser back. So cumulonimbus mammatus, CB mammatus, just beautiful, beautiful clouds on the underside of these cumulonimbus clouds. And they indicate very, very severe weather. I mean, you're getting some severe thunderstorms generally when you see these mammatus clouds. With thunderstorms also, of course, you get the thunder and the lightning that are present. Lightning may not always be visible. You might actually hear thunder on the distant horizon. You also may see that lightning on the distant horizon, so in a low, muffled sound of thunder. The lightning is just simply a discharge of electricity, by the way, that can heat the air. Look at this, 30,000 degrees Celsius. Lightning can heat the air up to that level. That's just incredible. The heating causes the air, this is a very rapid heating process in the atmosphere, and it causes the air to expand explosively, and that initiates the shock wave that we commonly hear as thunder. And by the way, you can basically determine how far away a lightning strike is by watching the lightning flash and then counting the number of seconds between the lightning flash and the clap of thunder. So let's say you see a lightning flash, 5 seconds passes, then you hear the thunder. That lightning strike was about 5 miles. Let me get this right. You see the lightning, 5 seconds. It was 1 mile away. There we go. Sorry, I have to really think things out sometimes. So 1 mile out, lightning. Then you hear thunder 5 seconds later. Lightning. You hear thunder 10 seconds later. It's 2 miles away was the lightning. So you can basically use that rule to determine how far away the lightning is. For every 5 seconds between the lightning and the clap of thunder, it's 1 mile. Here's some additional information about thunderstorm characteristics. Precip's usually brief, scattered or showery outside of slow-moving thunderstorms. The low-level wind shear, the change in that wind speed or wind direction over a short distance, is quite common with thunderstorms. And that's a big problem around airports. There's been a lot of aircraft accidents, unfortunately, when the pilots are trying to make a final approach to a runway, and you run into a downdraft or this crazy low level wind shear, lots of changes in wind speed or direction over short distances. Microbursts are strong localized downdrafts. When we say micro, we're thinking smaller here. So microburst is a type of localized downdraft. It's relatively small, less than 4 kilometers wide, that occurs beneath a thunderstorm. Macro bursts, macro being large, a large type of downburst, are over 4 kilometers wide. So to determine between a microburst and a macro burst, you really look at how wide are these particular downdrafts. And with thunderstorms, of course, the big thing is you can get tornadic activity and hail can occur. One of the biggest hazards that we have with thunderstorms is a tornado. And this is simply a violently rotating column of air in contact with the Earth's surface. If it's not in contact with the Earth's surface, it's a funnel cloud. Okay, that's the difference between a tornado and a funnel cloud. A tornado the tornado is in contact with the Earth's surface, while the funnel cloud is not. All right. And tornadoes most frequently are going to occur in the springtime when you get the big time clash of air masses. Winter is still trying to hang on, so you've got colder air, CP, continental polar air coming down from Canada, meeting maritime tropical air, very warm and muggy air. And where those two contrasting air masses meet, that's usually where we see a lot of tornadic activity, specifically in the plain states, southern plains, Oklahoma, Kansas. The overall topography is flat. So there's really not much modifying these contrasting air masses. They're kind of just meeting head on, and that results in some explosive supercell type thunderstorms and potential tornadoes. The average diameter, by the way, of a tornado is generally ranges from 300 feet to 1,800 feet, and they generally form in front of an advancing cold front or a squall line. Tornadoes are usually steered by southwesterly winds, so you'll see the tornado's common direction of movement is from the southwest to the northeast. The average speed of tornadoes is about 35 knots, but some tornadoes have been clocked up to 70 knots. This is an extremely dangerous situation with tornadoes because they can move so quickly, and it gives the general public such little time to take shelter. That's why it's always important to have a NOAA weather radio or really have a way to get the latest warnings on short notice. With waterspouts, really, this is the water version of a tornado. Okay, waterspouts, a rotated column of air over a large body of water. They're in contact with that water surface. Tornadoes are over land. Waterspouts are over water. They're much smaller than the average tornado, and they usually are less intense as compared to the land-based tornadoes. For severe thunderstorms now. So now we talked about the ingredients for basic thunderstorms. Now let's talk about the severe thunderstorms. Now, a thunderstorm that is severe has specific criteria here. One or more of the following must be present to be classified as a severe thunderstorm. This is directly from the National Weather Service from NOAA. Surface winds of 50 knots or 58 miles per hour or greater. Hail 1 inch in diameter or larger. So either of these conditions are met, it is a severe thunderstorm. Now the formation requirements, the wind aloft must be strong enough to tilt the updraft. Strong winds aloft keep the updraft free of any precipitation. Dry air in the middle levels of the atmosphere. You get upper level divergence or removal of mass aloft. Significant moisture in the lower levels of the atmosphere. You got vertical wind shear in the vertical throughout the entire atmospheric column. And then I want you to think the acronym SLIM, S-L-I-M, for severe thunderstorm requirements. What was missing in the basic thunderstorm formation was wind shear. But with severe thunderstorms, we have shear, we have lift, we have instability, and moisture. So that's SLIM, S-L-I-M, shear, lift, instability, and moisture. That shear is going to allow for rotation of updrafts. The longer lasting severe thunderstorms are longer lasting than an air mass thunderstorm counterparts. All right, so a couple of differences here between severe thunderstorms and just air mass thunderstorms or just your average thunderstorm. We have the winds aloft are stronger, which allows the updraft to be tilted. When you have an updraft that's tilted, the heavier rain that falls from that severe thunderstorm is not going to fall right through the updraft if the updraft's tilted. So that's going to keep the energy into that particular severe thunderstorm. And again, just think of the shear aspect. Lots of moisture, of course, and the vertical wind shear. Maybe a change in wind speed or direction with height. All right, that wraps up my video on, this is Severe Weather Fundamentals Part 1. This was on convective severe weather. So we talked about thunderstorms, and we talked about, some of the offspring of thunderstorms, tornadoes. We talked about the water spout over water. We talked about some of the essential ingredients necessary for thunderstorm formation, lift, instability, and moisture for your basic thunderstorms. For severe thunderstorms, shear, lift, instability, and moisture. And we talked about some of the characteristics of thunderstorms, thunderstorm types, and we talked about the stages of thunderstorm formation as well, the cumulus stage, mature stage, and dissipating stage. We talked about the different types of convection, free and forced, and we analyzed atmospheric stability. You look at the air parcel's temperature, compare it to the surrounding environmental air temperature. If the parcel is warmer than the surrounding environmental air, it will continue to rise. The atmosphere is unstable. If the air parcel is colder than the environmental surrounding air, it's going to be colder, it's going to want to sink, it's going to be more dense, indicating stability. Here's your acronyms in the atmosphere. Warm layer over a cold layer in the vertical equals stable situation. Don't tip the cow. Colder air over a warmer layer is unstable situation in the atmosphere. And that is all I got for now, everybody. Certainly hope you enjoyed Severe Weather Fundamentals Part 1, and I will be working to put out Severe Weather Fundamentals Part 2 in the next training video. We're going to cover things such as snowstorms and blizzards, anything that's non-convective related. All right, that wraps it up, everybody. I thank you for your attention. I certainly hope you enjoyed the presentations. And until next time, take care and God bless everyone.